So great, guys. So now let's kickstart the session.
Today we have an exciting topic of Internet of Things. So on that too, we are planning to show some interesting simulations as well, so that you can try that back at your side, back at your home, and these can be a very good kickstart if you are doing in your third years, or if you are at your second years, or if you are so keen to understand more about this IoT as a technology, and how you can build your own small circuit. This workshop would be a great start for all of you. So today's learning objective is very clear. At the end of this session, the participants will understand the need of IoT, and they'll get familiarized with some of the uh, existing free tools or simple simulators based out of ESB boards and ESP8266. So we'll do some small projects on ESP8 based boards in the simulator, and we will try to build some IoT application. So that's the kind of workshop that I'm planning to conduct for next 2 hours or 3 hours. So before we get started, let's try to understand what is Internet of Things. So the word IoT is a buzzword today. Every one of us know. IoT describes that in a network, if you are connecting a embedded device or embedded electronic device that is equipped with some sort of sensors and transmitters, so that it can communicate certain information to the cloud or extract some information from the cloud, then these are called as IoT systems. So IoT is not something that's I would say it's very very new. The word IoT has been made as a buzzword because people started connecting everything with internet, every device with internet. On a larger scheme, if you are asking a equivalent engineering term for these kind of things, uh, in the olden days it's called as pervasive computing, where you can compute from everywhere on everything. But now uh, later it was called or recoined as IoT. So as human can speak, listen, they communicate, they pass information. In the modern era, we have things, we have devices which can talk, which can communicate, which can exchange information. Some best example for a successful IoT product is your Alexa. Everybody is using Alexa and seeing the potential benefit of it. So you can connect your fan, you can connect your AC, you can connect digital lights. So many things you can do by connecting it with the internet. By doing so, we gain control over that devices. That's a major key advantage, as well as we have some sort of ownership and some sort of easy connectivity, some sort of information exchange from them, so that we can do live monitoring, so that there would be enormous amount of application when it comes to the IoT. So here is an interesting information. Whatever that you see in the x-axis is the year, and y-axis is in terms of devices, billion devices that are connected. So say for example, somewhere in 2020, we have close to 11.3 billion devices connected to internet. But in 2030, in this end of this decade, we are anticipating that this number will go almost triple times, which is where we'll have close to 30 billion devices coming to connect in the internet. So this is not information that's given by Skill-Lync. It is derived from an authentic source. So we are seeing major devices. We are going to see connected cars. We are going to see multiple other applications where the information coming from the connected cloud is a key thing, and it's going to be important. So what made IoT possible? Why people are so keen on the IoT now? Because with IoT, our IoT is achievable. One is we started fabricating, or we started producing very low power sensors at an affordable price, which means in all your devices can have low cost sensors, and since it's manufactured at a very large scale, we can get it at a very, very affordable cost. So just to give you an example, every one of us who is holding a mobile phone for less than 6,000 to 8,000 rupees, even that particular device has got enormous amount of sensors. Then other big advantage is because of higher data rates in India or across the globe now. Particularly in this generation, we saw 4G, 5G uh, opening up their frequency, and we are having a data availability in our handle device at a feasible or affordable cost again. Whereas it's not the case. 10 years prior, we do have 2 GB given at a daily quota. So we have seen ages where in a mobile phone you use only 2 GB over a month. So those things were gone, and we have easy availability to many cloud platforms through which you can connect, you can fetch some data, put some data, as well as many advancement in machine learning and data analytics that makes the data collection as a meaningful thing. What is the point in connecting or acquiring data from multiple resources? So through that you can do some sort of analytics, you can conclude or you can gather some information. So this is again possible. This advancement of data analytics, machine learning technologies is also making this IoT technology more interesting. When I say I'm just logging sensor at a rate of 100 data per second or 1,000 data per second. So these many samples, what am I going to do with these many samples? So I need to do some sort of analytics, or I need to build some sort of machine learning model from the data acquired. So there is a measurement unit going down. Way for sending the data is also going down. Feasibility of storing the data is also available, and trend of analytics or tools for analyzing the data is also available. These are put together a package, put together making IoT more interesting in recent times, or more applicable, more relevant in recent times. So these are few standard architectures. Excuse me. Few standard architectures that is followed in IoT. So one is you have multiple nodes in IoT terms. A device or a thing, or what we say as thing in T or thing in IoT. So that has a feasibility to connect to the gateway, which means I can have node 1, node 2, node 3 connected to a gateway. So this gateway will allow us to connect to the cloud or to the internet through some sort of API, through our whether bypassing a firewall or without using a firewall. And there is a access point which is actually giving access to the gateway to reach the internet. So it is very similar to your PC now connecting to an internet. It's as same as that. So once my nodes are connected to the cloud, I have access to all these. I have access to cloud storage, I have access to server, I have access to private or public cloud, I have access to some applications that is hosted onto the cloud, I have access to the database, I have access to the mobile phone. So through internet, all reaching out to all these are possible. So whatever that you play at a node, you can take that till the cloud. That's the whole objective in the IoT. So this model is called as a centralized network. So instead of centralized network, we have something called as a peer-to-peer network. So in peer-to-peer network, where we are enabling internet without the gateway, directly our nodes are connected to the cloud. So this model is called as a peer-to-peer network. So what is the framework here? So let's see the typical component or usual components, I would say, that formulates the framework of IoT. One is node. Node is the final end device which collects the data from the user or which collects the data from the environment. Let's say, for example, if you are using Alexa, Alexa can be a node because that's connected to cloud through our internet, and that's interacting with us, that's collecting data from the user. Or let's say, for example, you have connected your air conditioner HVAC system to AC, or you have connected your car to internet. In all these cases, car becomes a node. Your HVAC system becomes node. Your air conditioner becomes a node. Okay. So most of the time, it will be having the node will be having a IoT application running on a CPU. Then you have master or IoT application. Usually, it's good to call it as IoT application so that there will not be any confusion. So IoT application basically it integrates the data received from various nodes, as well as it uses some sort of information extraction mechanism, because it is actually pulling up all the information from multiple nodes. Then we have something called as graphical user interface. This final graphical user interface um, displays some information, or via this some sort of actuator control. Actuator can be controlled. So the GUI is the final end device, or it's a HMI that we are giving to the user for varying some information in the whole IoT framework. So let's see some use case of IoT in the different sectors. So if you take IoT, it can be applied in commerce, finance, where you can have a IoT application or a device that's monitoring, it could be a simple app that is helping you to monitor the stock prices. Starting from that, it allows you to interact on a live basis, or it can be a healthcare product where some sort of glucose tube or glucose wall can be opened, closed automatically. And we have infrastructural requirement, or commercial or industrial IoT is very, very popular, has got enormous application. So commercial, in terms of, assume that you are connected in a vehicle with this IoT features, and you are entering into a new infrastructure. So vehicle to infrastructure communication becomes possible, and you see suddenly an ad playing when you reach that infrastructure. So that could be a commercial application. So there are a lot of possibilities and a lot of application. It opens up a lot of venues in different areas where you can use these IoT applications. So here are some examples under each sectors. If you take smart cities, we have smart lighting, where your street lamps lighting units can be remotely controlled, and automated parking lot, pollution level checking, waste generation. In the manufacturing or industry time or industry IoT, we have work in progress monitoring, we have prevention of unplanned downtime, and production quality improvement. All this can be achieved with IoT. And then data driven healthcare. So as I told you, we can re-diagnose some disease, we can monitor the patients, and we can turn on, turn off some valves or something with that is given along with the patient. Then connected logistics, very common. We have seen all this, all the buses installed with a speed meter, where if any driver is exceeding 60 kilometer, it'll show that information. And we have all seen apps like Ola, Uber, where you have a live tracking of the devices. It all made possible with the IoT technology. So you can track a package live location. You can predict the estimated time of arrival, and many things again on the logistics we can automate with IoT technology. So in simple IoT in the healthcare, passion monitoring can happen in several ways and in several facets, I would say. Medication intake tracking, remote health monitoring, and medical inventory equipment and tracking, drug tracking. All these can be done with healthcare applications of IoT. Now, what kind of hardware is used? So again, I'm not saying these are the only hardware. or I'm not saying that these are the what do you call. So this is the final way that you can implement IoT. This is a very first step. If you want to start your career with IoT, if you want to try out something with IoT, you need a smart device which can perform a decent computation, as well as which allows you to interface multiple devices. Along with that, which allows you to connect the node to the cloud. So with having all this requirement, ESP8266 or ESP32 is a best prototyping or low cost prototyping platform where you can immediately bootstrap your application or rapid prototype your application with a given libraries and with the simple hardware set. So what is this ESP32 or ESP8266? Basically, it is a SoC. SoC stands for system on chip. So this is from a semiconductor provider called as Express F Systems, and it gives Wi-Fi, dual mode Bluetooth connectivity, and for IoT based projects, ESP8266 and ESP32 are controllers that are preferred actually. So among them, among this both ESP8266 is low cost, low power SoC chip series. So basically, what are the functions? So yeah, ESP8266 or ESP32 can perform the following operations. It can either perform networking. When I say networking, the Wi-Fi module, there will be a Wi-Fi module which enables to connect to the routers for transmitting data. The first example or the first functional use case. The second functionality is with this you can able to perform, you can do data processing. When I say data processing, you can, this has a lot of peripherals since it's an SoC. This SoC has got a lot of peripherals like common peripherals like GPIO, analog to digital converter, PWM, serial communication, and even it can perform some complex operations with the help of a real-time operating system, which means this SoC will allow you to port some sort of real-time operating system using which you can create some parallel task and you can avail the features of an operating system. So all this data processing can be very well done on both this hardware. Then we can go for P2P connectivity as well. We know the peer-to-peer is one popular architecture in the IoT. So basically with this, we establish a direct communication between different ESP devices or one ESP with the other devices in the whole IoT. Then we can host or can access web pages that is written in HTML or other languages. So you can host a web server at a very lightweight web server again. So most common IoT applications that we do with this is you can have smart energy application, you can have smart medical application, or you can have a smart industrial application. All these things are possible. So here is a block diagram of the ESP8266. So where as part of the microcontrolling features, it will have SRAM and flash followed by all these interfaces. So it supports serial data, input output, SPI, ADC, then I2C, I2S, GPIO, GP, UART. Then we have a media accelerated controller which has the core CPU registers. Then along with that, it has a digital baseband device which helps you to interface with the which basically helps you to do some sort of communication. So on top of this, you have all the analog receiver, RF receiver, analog transmitter, and there is one voltage control oscillator and one PLL. So putting this together, you will have the entire ESP8266 on one single hardware. It looks very handy like this. So typically, this is what the pin details of ESP8266. Here you could see certain pins that are used for GPIO, certain pins that are used for analog inputs. There are certain inputs that are used for serial in, serial out data. So typically all the functionalities that we do with microcontroller can be done. Along with that, you can do other functionalities as well. So now we have seen the ESP8266 block diagram. Here is a slightly an advanced version, which is ESP32. So ESP32 SoC is actually powered by single core or dual core 32-bit microprocessor. So it's from LX series of Extensa. Then it has all the peripherals along with other peripherals, which is not there in ESP8266. It has TWA as well as it has touch sensor. Then it also support Wi-Fi MAC, Wi-Fi baseband. It also has Bluetooth connectivity feature when it comes to P2P architecture. Also, there is a cryptographic hardware acceleration unit, which enables technology like AES and SHA for you to do some sort of hardware level encryption, because the communication is happening, which has to be secured. So with ESP32, you can go a bit more complex in your calculations, in your data processing, and it also supports the cryptographic based hardware acceleration. I'll pass for a while here. If you have any questions, please feel free to post it here. If not, I'll continue. So I could see, okay, good to go. I could see somebody commented that the voice is not clear. Mehul, can you confirm, am I audible enough?
Yes. All good, Jagan. Not an issue.
Thank you. Thank you. Ritesh is raising his hand. If you have any question, please post it on the chat window. Amit Zimpa is asking, how can we use IoT for industrial application? Yes, I think I have answered your query. So if you take applications like you want to do apply it in a manufacturing industry, so you can have a device which monitors the progress, and you can have unplanned downtime can be avoided. Let's say if somebody is not there, the device automatically monitors and stores the data or updates something. Okay, so there were questions on what is SOC. So basically, this is a major application in when it comes to industry. Or when you want to open a wall, when you want to automatically close a wall from a centralized place, and when you want to control some pressure, or you want to measure a parameter change for a given period of time, all those things can be incorporated. SOC stands for system on chip, which means I'm packing a entire system. I'm packing an entire system onto one IC, and it's more than a microcontroller. I will not say it is a microcontroller. It is more than a microcontroller with more better features. Yashwant is asking, will all electric vehicle have same architecture? I feel uh, is the question is wrongly asked. With respect to IoT in electric vehicle, yes, everything will have a same architecture. And it's, as I told you, it is more than a microcontroller. So it's ESP8266 and ESP32. Yes, as I told, ESP32 is the latest version, quite costliest, as well as it has more computational capability. It supports Bluetooth connectivity, and it has dual core as well as cryptographic feature enabled. So Muthu is asking, what is the difference between an IoT and embedded system? How Arduino is used in both, or what is both? Is it same or different? Muthu, it's an interesting question. Uh, See, any embedded system that is connected to a cloud is an IoT system. It's IoT. We can say that as an IoT. Or I can put it in this way: uh, it doesn't need to be an embedded system to be connected on internet. It either can be connected or need not to be connected. So if it's doing a generic functionality which has a hardware software, then in that case it is called as an embedded system. Any embedded system which is mandatorily connected with the internet, it is IoT. So now you can say that embedded system. So embedded system IoT is actually a subset of an embedded system which belongs to only the connected family. So you use Arduino or you don't use Arduino, that's up to the developer. It's all about having the whole system connected to the internet. So what are different alternative ESP boards for IoT application? There are so many other, it's not only ESP boards, you have other family of hardware. You have, like you can consider starting with Raspberry Pi, any form of hardware which you feel it's enabling you to connect to internet easily. All those can be used for IoT application. Again, Amit is asking, how can we implement IoT in transportation and railways? Let's say, for example, I'll give you a project idea. You're taking GPS coordinate, and your device is automatically identifying what is the current location of the train, and it can read what is the velocity and the train is going with based on the sensors that is connected. So it's matter of GPS, and it's matter of estimating velocity from GPS or estimating velocity from accelerometer. We can say, we can calculate on this device, can send a centralized or put a centralized display saying that your next stop or your next point is will be reached in so and so time. So it can calculate ETA. It can, with the GPS, it can say where are we currently now. So it would be helpful for many new members, many new customers they are traveling. Or this is one application in railways. You can think of several lot of applications. So it would be really having more potential usage in transportation industry. How is SOC is different from MC? SOC has more capability as a system. When I say as a system, uh, microcontroller might not have inbuilt feature or inbuilt system features, whereas this will tend to have inbuilt system features. Which means, for to give you an example, it has by default in the architecture, or in the chip itself, it has a Wi-Fi transmitter, whereas a microcontroller typically will not have that. It's an add-on device you have to connect separately. Amit is again asking, what is the difference between IoT and BMS building management DC? I think DC control. Let's not confuse this with IoT with your electric vehicle terms. BMS is for battery management. DC control is again for I would say a device that is there in the electric vehicle to control the voltage levels. So IoT is something that's completely different, which is there in which can be incorporated in multiple devices, where you can leverage your device feature by connecting it to internet. How ESP8266 is different from ESP32? I think I have told the differences. Can we get an analysis if we do RC car with ESP? Yes, you can. Does IoT technology has a significant role in medical devices? Yes, we have seen an example where a patient can be continuously monitored, and a patient can be diagnosed automatically. His whole pattern can be suggested and monitored with the help of the IoT systems. How can we implement IoT in driverless technology for EV and automation, agriculture applications? I think we are jumping cards here. IoT can be implemented in either it be uh, EV or driverless technology, yes, it can be implemented everywhere. Similarly, the architecture remains the same. So Vishnu is asking the same way. How do you get there are multiple web servers to which you can able to upload the data that you are acquiring from your RC car through ESP. So you can use ThinkSpeak. So ThinkSpeak is one popular free dashboard which helps you to visualize the value that are which helps you to visualize the data that you are acquiring from your ESP node. So to answer Vishnu's question, I think you can go explore more about ThinkSpeak. ThinkSpeak is a simple dashboard. What is the difference between, again, it's the same question. Whether can we make automated vehicle with, yeah, we can. All those things are possible. Okay. I think we have taken enough questions. Let's, if we have other questions, we can park it at the end. So with this, now here is a comparison of ESP8266 with ESP32. So you can able to see the difference. So the, the core MCU comes with dual core in ESP32, single core in ESP8266, and Bluetooth is not available in 8266, whereas it's available in 32. And we have our typical frequency is also doubled, and SRAM capability is way beyond, and it has more GPIOs, it has more PWM channels, it has more better resolution ADC. Everything is almost doubled when it comes to ESP32. So with having said that, now let's move on with the simulator, and we will try to build some small circuits, and we will try to write some small code so that we can simulate our ESP device online in a cloud platform. So you need not buy the ESP device by yourself to do a project. So you can easily simulate that using this kind of simulators. Oakview is one such online simulator. Let me take you through the interface. So just go to Google, search for Oakview. You will get this online simulator. So with this, you can simulate many devices, and it's a community. You can discuss with many members, and you can it has some quick start template also. So you can build small circuits, you can build, you can test all those things online. It's very easy to use. So if you want to start something from scratch, it allows you to use or simulate an Arduino device, or a Mega, or a Nano, or Raspberry Pi, or you can use MicroPython on ESP32, or you can simply use an ESP32 with Arduino libraries. So I've just used clicked ESP32. Now I have this device. So here it's your simulation window, and this is your you have three things. You have sketch INO, you have diagram.json, you have library manager. So sketch INO is a place, it's kind of an editor where you can write your code, and you can flash the code onto the simulation ESP that is running here. And if you want to add some new library, so we will be adding some new library that can be added by just clicking this plus, and you can search for the library, and you can add the library. So this is about the editor. So here you have some interesting buttons which allow you to zoom or have a grid, a turn on, turn off the grid. So you can do all these things, and you can fit the circuit in this given uh, size, and you can add enormous amount of components. So starting for display, it offers you many devices, and for input, it offers you many devices. For sensors, it offers you many devices. So these many things can be bought in, and you can add. This is about the Oakview simulator. Now let's attempt to do one simple simulation so that if you want to practice on parallel with me, you can also do that. So I'm going to build this kind of small circuit, as well as I'm going to build, write this code and make this whole thing run. So if you have OK simulator, if you have this environment running, do the same step along with me so that you will also have same output produced. Now what I'm going to do is I'm going to turn on, turn off a digital circuit or digital IO. So we already know the pin diagram details. So with having that, now I'm going to add two components. One is an LED. So LED is added. I want to add a resistor. I have added a resistor as well. Now what we can do is let's take this particular line and connect it to the ground. So let's have, or you can connect it via an LED also, a resistor also. Okay, I've connected to the ground. Now I have the other pin. I'm connecting that to pin D2. So if you click here, it will show the pin number, it will show the functional usage. So I have connected a D2 to my LED. Now this is how a simple circuit, digital circuit can be made. Now let's come to the coding part. So in the typical coding part, now we are going to have two loops. One is called as setup, which will run only for once, and you have the loop which will continue to run for multiple times or over a period of time. It will never stop as till we bring the power down. Now under void setup, I'm going to say, I'll remove all this. I'm going to say what is the pin direction. So we have used, our LED is connected to the second pin. So I'm naming second pin as LED. Now here, let me say my second pin is a output pin. So the name of I've given to second pin is LED as output. So this is so easy to code this interface. So it will give you the tips and tricks if you start putting the APIs. So now we are going to toggle the LED by writing value to it. So I'm just writing LED's value as I, then followed by a delay of, I'm going to give a delay of 1000. Then let me write again. This time let me turn it off. Then followed by a delay. So in the simulator, you can play much more things. Now the code is also ready. The circuit is also ready. I'm just going to put the start my simulation. So the code will get compiled and the compiled code will run on the circuit that we have built. So what is the mistake that I have made? So I want to turn off after 1000 millisecond, but here also I made it as I. Now I've corrected it. So you could see it is blinking for every 1 second. So here you see what is the time the simulator is running. It is almost on par with the real time. So, but still it is hosted in the cloud. There might be some delays also that you will be facing. So already the inbuilt LED is also connected to the second pin, so it's also blinking. So please post if you can't able to do, or you can't able to do this output. Yeah, if you have any queries on getting this, please let me know. To answer Sharon's question, yes, we have planned it as a 3 hours workshop only. So once you have done, this is the best way you can start. This is how you can start a small uh, circuit at your side with no zero cost, with less effort, and you can kickstart doing something with the ESP32 hardware very simply. So Akash Ruben is asking, can you repeat the step once? Okay, I'll repeat it. Akash, please listen carefully. So the circuit is built on this side. What I have done is, while opening, let me open a new interface of Oakme. I have just Googled for Oakme and I have opened this simulator. Here, you have to come down and you have to click. If you want to start a project from scratch, you want to pick a device from where you want to start. I'm using ESP32, so I'm clicking this. So by default, this window will come. After that, by clicking add new part, I'm bringing LED and I'm bringing a resistor. Then I made a circuit that is shown here. I made a circuit that's shown here where I have connected one end of the LED terminal to the ground, other end to the DIO interface, so that I can turn it on, turn it off. On the coding side, I have made number 2 as LED because I am going to use pin 2 as LED. Then on the digital right side, sorry, on the loop, I'm calling a function. These are Arduino APIs, which is actually supported by ESP32 also. So we are actually writing a simple API, Arduino API, and we are making an LED to glow. That's it. So this is a very, very first step anybody can start with. So what are the APIs that you can use simply in the ESP32 environment? So one is you can use pin mode, as we have seen the usage of pin mode that allows you to set an input or output side, and you can use digital write, digital read for a DIO peripheral, and analog read, analog write for a ADC peripheral. The syntax has given there. This API delay allows you to generate a delay. Then millis allows you to generate uh, time delay in terms of millisecond. Micros, serial dot begin, serial dot print, serial dot available. These functions allow you to uh, set the serial data's baud rate, uh, as well as allows you to transmit a serial message, which you can see on the serial monitor. Then we have a serial dot, a servo dot attach, servo dot write. These functions, are these APIs are there for I would say for when you use a servo motor, you can use these APIs, readily available APIs, which will help you directly to control the position of the servo motor. So you can directly pass the motor angle degree to your API and you can able to control. So Now let's move ahead with the next topic, which is on LED and relay interface. Okay, this is so what we have seen in the previous LED exercise. It's just a blinky LED exercise, which allows us to uh, make our get us comfortable with the interface. So we have done that. Now we will start building some interesting circuits and some small programs. Then we will move ahead with the with actual IoT application. I would say with having an MQTT server, and where we will publish some message into a web page through our IoT node. We will somewhere end this whole webinar by establishing a MQTT connection, which is very popular protocol used for data exchange between the cloud and the node. We'll do that and we will wind up. Now let's go ahead and build other circuit. Now this time it is going to be interfacing a relay and a LED. Okay. So we know LED is a semiconductor device. It has anode and cathode. The bigger pin is anode and the shorter one is cathode. We have used that. So we are going to build these kind of a circuit, which is very common, straightforward LED circuit. You have to connect the LED in such a way along with a current limiting resistor so that it doesn't get burned. And during forward bias, it will work, or it will glow. During reverse bias, it will turn off. We have seen this. We have interfaced also. Now let's go ahead and do one more thing. In the real circuit, this looks something like this. So if you have a breadboard and if you have a real ESP32 hardware or ESP8266 hardware, you can connect and you can try out this circuit. So here is a small exercise that you can able to build, or I'm giving for you to try. Design a running LED using ESP32, which means let's connect 4 LED, and you have to turn on first LED, then turn off it, open, give a delay, and turn on the second LED. Then after a delay, turn off the second LED, turn on the third LED. So that it looks like a chain of LEDs turning off and turning on and running. So try to connect a LED circuit like that. So you can connect multiple LEDs in series to do that, or you can connect each one LED to one DIO pin so that you can turn one LED, turn off one LED, turn on other LED. So that's the best way of creating LED, running LED. If your ESP32 has got 16 GPIOs, try it with at least 4-5 LEDs. So you gain some more confidence. Then you can attempt a 4-bit counter, making your display or making your LEDs itself. You can count starting from 000. So in the binary format, 0001, 0010. So I can have a switch, and I can, based on the switch input or based on a constant delay, I can increment. I can create a 4-bit counter with 4 LEDs, or you can even count a 3-bit counter with 3 LEDs. So this is again an interesting project to try. Now let's try to understand the relay. So relay. Now we are going to do a next circuit where there is a relay, and there is also a LED, and this time we are going to use our relay and the LED combination based circuit. So basically, a relay is a simple electromechanical switch. It's not there is something called a solid state relay, which is a semiconductor device. But on a normal relay, it's a electromechanical switch only. So you will see a switch opened or switch closed. We are going to actuate the switch opening or switch closed condition by applying some sort of electrical input. So normally switches are used to close or open a manual circuit, whereas if you connect relay, this can be automated. So instead of manual operation, you can give electrical signal. The core principle in that is there will be electromagnetic. So that electromagnet will help you to attach or will help you to detach. I'll I'll show different configurations that you have on a relay. So as per the constructions, a relay, it's very similar to your home switches, home manual switches, but instead of manual switches, we have these kind of configurations. You have single pole, single throw relay, which means a pole and throw can be equated with input and output. A single pole throw is nothing but you'll have one input, one output device. A single pole double throw is kind of one input uh, can be connected, or it's like you have two outputs. You can either connect your input to output one or output two, or you have a double pole and single throw. So again, it's used to connect two terminals of the devices. So you can have two control switches for having one uh, actuator to turn on, and double pole double throw is possible. So the example in real world that most of the time we use in relay is SPDT, and in simulation DPDT is shown. So this is how internally it looks like. Uh, so normally opened where it would be connected here, normally closed it would be connected here, and we'll be switching between these two. So here is a device. You can able to see if you connect in this particular configuration where these two pins are connected, or this two pin is helping you for actuation. This is connected to the ground, and this is connected to the input VN, and this is connected to your LED. So now what happens whenever I turn on this DC5, only then the LED gets turned on. So if you can able to see LED is connected to 26th pin, whereas my relay is connected to, sorry, yeah, sorry, this is the 26th pin, which is nothing but it should be a LED switch, so that you don't get it confused. So whenever I turn on this 26th switch, only then the LED will glow. If not, the LED will not glow, because the switch for LED is there coming from this configuration. So this switch is nothing but you have these many terminal KSC to DC5. It has these configuration where uh, you have C1, C2 as well as NC1, NO1, NC2, NO2. So that's why you have these many pins. So this is on a relay interface. I'm just keeping the screen for a while. If require, you can take a snapshot, or if require, try the circuit. So once you have tried, please put it in the chat. Okay, there are few questions. Can't we simulate CC3200? I have not tried myself simulating CC3200. Can we install two or more LEDs? Yes, Nikhil, we can install. So how many LED that you are interfacing? Each LED has to be connected to the a DIO platform. So Anam is asking, will you explain about Arduino IDE also? If require, yes. But in the simulator, you don't require, for doing everything in the simulator, you don't require Arduino IDE. Anam is asking, can you explain this again? Yes, Anam, I'm going to explain again. So basically, relay is a electromechanical switch. It's very similar to this configuration where there is a coil. If you are energizing the coil, there will be an electromagnet or which gets actuated. So what happened? Your switch becomes normally closed. Your switch will go to the closed position. Uh, and when you de-energize the coil, the switch becomes open. So there will not be any physical contact. So you can either keep your switch connected to the common supply, or you can make your switch connect to the uh, or you can make the switch to the open condition, so that no connection between the load and the common. So that's what we are doing in this what do you say, in this circuit also, where I'm connecting my relay to 26th pin. So my relay is grounded and input for the relay is coming from 26th pin, and my relay coil is getting energized by the Vin input. So whenever I turn on the 26 pin, output or the switch will go to the closed position, so that I will have my LED glowing. If I de-energize just by turning off this, then my LED will turn off. So it's a very simple example, uh, where you are either energizing the coil, de-energizing the coil by giving a low power signal from the controller. Let's try to build this particular circuit. So this is more interesting, where we are going to read a switch status. So now what we are going to do is we are going to have a button and a LED interface. So this is how a button can be interfaced. Again, what we are doing is we are having a GPIO on which I'm connecting my button's ground, as well as the green line is going to the button input, and the input is going to the D5 pin. And there is an LED which is again whose line is connected to ground, and this is connected to the D5 pin or D4 pin. What I'm going to do here is I'm going to make this push button, or make this input, or make this LED toggle every time, which means if I press the button once, it sees the previous states, or it sees what is the present state uh, of the button. And then if the present state of the button is high, it sets the LED as high. If not, it will set the LED as low. Very simple. So unless until as long as I hold the button, I will have the LED glowing. Let's go ahead and try this circuit with me. Let's build this circuit together. So let me still have the same electrical circuit as such. Delete all the lines so that I can use the code in such a way where we are connecting. So LED is connected to D4. So LED is connected to D4. Now this is connected to ground. Done. Then we'll have a push button. Push button is here. If you want a quick help, I recommend you to click this so that you will see what are the pins, how it is internally connected. You can get that view also just by clicking this question mark. So now this side is connected to the ground again. And this is connected to the input. In our case, it is 3.3 volt. And this pin is connected to D5. So my circuit is ready. It's very simple circuit where you have to connect the switches and you have to connect the LEDs properly. That's it. Once you have done that, now let's go ahead and change our code according to your inputs. So LED is connected to 4 and my button is connected to 5. So let's put those things in a way, and LED is marked as output, and pin mode is should be marked as the input. Done. Now let's come declare the variables. So one is I want to read the present state. So let's have a button. Okay. Before that, I'll have the variables declared. Let me call that as button status or button state. So button state is equal to, I'm going to digitally read which pin number. It's pin number 5. So or I can put digitally read the button because we have made that as pin number 5. Okay. Now, depending on this value, I'm going to either turn it on or turn it off. Straightforward code. If button state is high, let's make your LED as high. It's better to use curly braces so that you don't make any mistakes. Okay, fine. So this is our simple code. Let's see what is happening in the simulation. If I missed anything, it would be visible. So whenever I press, as long as I hold, it is glowing. When I remove my toggle, it is coming back. So it is continuously reading the button state as long as the loop is there. If it is high alone, whenever there is high, it is blinking. Whenever the high goes down, it is going to low. So if you want to make this a bit more presentable, you can add a delay of 1 second. So it makes. So the point here is, now this delay will also act like a debounce delay. So it waits for 1,000 seconds in the else also when LED goes down. So now you could see, as long as I'm pressing, the LED is actually glowing. So this is how you make your button states get updated every time. So if you guys have any queries, please do let me know. It's again other simple exercise on the whole demonstration was to explain you what is the use or how you can use digital read, how you can create this kind of simple circuit. Again, now we have not used a relay, rather a relay, we have used a switch. Go to this help. So this is how the push button internal contacts would be. So it's when I press it gets connected. When I uh, leave it gets disconnected. So internals is very simple. So that is why when I click this, I have built the circuit in such a way that this terminal is giving your power, and this is going to the switch state. We are monitoring this as the input, either to connect this particular line and this particular line. We are using this push button, as simple as that. I hope that is clear. Let's get move on. Let me get to the next circuit. So this is a circuit diagram if you want to interface in the breadboard, where the connection is also again very similar. You can connect your ground, and you can connect your source for the switch from the supply through this black and red line, and the input to the microcontroller can go from this one. And you have used resistor also. Now again, these are the exercises that I want to give. Interface to switch and control two different LEDs. So it's like now you have to build a circuit where you are connecting two different LEDs and you are connecting two different switches, and you can write your code accordingly, so that if you press switch 1, switch 2 glows, and if you press switch 2, switch 2 glows. And other one is you can design a program that where a switch can control the LED only after some 10 events. When I say 10 events, after counting till 10, so after doing something, or after a delay of 10 millisecond, the LED goes. So that can be one. And interface two switches and control the LED state, one for turning on, other for turning off. This also could be an interesting exercise. Jagadish K is asking, shall we try in Tinkercad? This is very similar to Tinkercad platform, but the difference or the reason for going for OakP is I don't think Tinkercad will allow you to simulate ESP boards. Whereas in Tinkercad, you can able to simulate all these in only Arduino based platforms. So ESP based platforms, you have to use OakP simulator. Now let's move ahead. We will do the next exercise. Again, my favorite exercise on ADC interface. So before getting into this ADC, let's have a quick look on the ADC theory part. Let me go there. So this is one interesting picture actually that demonstrates the whole functionality of ADC. So this is what happened at each stage of ADC. Say for example, there is a physical phenomena, which means physically something is changing, that is actually measured, or that is actually measured by the, or detected by the sensor. Now the variation is read like this as a noisy electrical signal. Why? Because this sensor could be a resistive sensor or could be a capacitive sensor. So depending on the nature of the sensor, depending on the physical phenomena, your transducer is actually creating something which will have noise, obviously, which will have noise. Now what we do is we use some sort of filtering circuit or some sort of signal conditioning circuit like clipper, clamper, amplifier, and op amp, so that you do something and you eliminate noise, you amplify the signal strength, so that you make that as a conditioned signal. Now you have the conditioned signal. So this conditioned signal, let's assume you are receiving this signal condition. Now you want to process this signal further. To process this signal further, we have to do three mandatory things. Because see, my microcontroller, I know for a fact it process only the software, digital data. When I say digital data, it needs to have zeros and ones to process. It cannot do it cannot able to process this kind of signal, this kind of physical phenomenon. So what we have to do is we have to break the signal in the x-axis as well as in the y-axis. So these two steps are called as uh, sampling as well as digitizing or quantization. So breaking the signal or the analog signal in x-axis is nothing but sampling. Breaking it again in the y-axis, it's called as uh, quantization or digitization. See, this is the basic principle behind any digital signal processing ideology. So once the signal is actually broken in terms of what do you say, the y-axis as well. Now we will go ahead and we will encode that data. Encoding is nothing but fitting that data on a prescribed level. So that each prescribed level will have a binary information, raw binary information associated with that. So this process is called as encoding. So the three stage of analog to digital conversion is very important. It is called as sampling, quantization, and putting that into a actual information, which is encoding. So once the raw binary information is received, we can have that information converted into a meaningful final value in our application software. So now what we are going to do is we are going to build a circuit which is based on an analog sensor. The analog sensor that I'm taking into account, or the analog sensor that I'm going to take for today's demo, is we will have an LDR. LDR stands for light dependent resistor, which means depending on the physical phenomena, depending on how much amount of light that is getting it onto my resistor, my resistor value changes. So if more intensity of light is hitting on my resistor value would be very high. If it is less, resistor value will change proportionally according to the light value, so that I can able to sense the range, or I can able to sense the light intensity just by finding the variation in the resistance. So now to substitute here, our LDR is going to give this kind of signal based on my light intensity. My physical phenomena is change in the light intensity. The signal that my LDR is going to provide us the change in the resistance value. Now I'm going to take that change in the resistance and I'm going to convert that into a change in voltage, because finally we want a voltage signal to be processed by our ADC. So I'm going to design a small transducer, or I'm going to design a small circuitry where there is a resistance variation in resistance is actually given in terms of variation in terms of voltage. So that's our signal conditioner doing here. Once I get that variation in terms of resistance, what we are going to do is we are going to sample that voltage values. This is very important step. If you didn't follow the Nyquist sampling criteria, Nyquist sampling grid, then it becomes very difficult for you to reproduce this original signal, which means you have lost some information. So that Nyquist sampling criteria is actually based on a simple point that you need to consider your maximum frequency of your physical phenomena change, and you have to sample twice the amount of that maximum frequency. So we know at what rate our physical phenomena is changing. So with keeping that in mind, we have to play with the digitized sample data, or we have to consider the frequency in such a way that always it should be twice that of the maximum frequency, so that we don't leave any data, so that we completely reconstruct it. Now my sampled digital data will look like this, which means I don't have the information between this nth second to this n plus 1th second. Let's consider the x-axis as time. Obviously it is time, and y-axis as voltage. Now I have changed my continuous time signal into a discrete time signal. I have information only for at nth second, n plus 1th second, and n plus 5th second, and goes on. I don't have information between nth second and n plus 1th second. Then we have chopping at the y-axis level. Now, what is happening? I'm just quantizing this signal. When I say quantize, I'm actually jumping from year to year, which is again as equivalent as chopping at the y-axis level. I've chopped at x-axis. Now I'm imagine that I'm chopping at y-axis. So once I have connected this, now I know the discrete set of levels at each stage. That level has given a binary name. So that is called as the encoding. So at each level, there is some error difference. That error difference is called as quantization error. So you can improve your quantization error by increasing the resolution, of your analog to digital converter. So if you increase the frequency of chopping in your y-axis, x-axis, that is going to increase the resolution in terms of, or that's going to have more sampled data, more processing, more information, uh, like more core towards your original signal. Whereas if you chop it y-axis and that chop has got multiple levels, you have better resolution. So the resolution comes with the cost of your ADC levels. So if it's a 10-bit ADC, we can have only 10-bit resolution. If it's 12-bit, you can have that many. So here I'm showing a demo of 8-bit values. So once the value is chopped like this, as time goes on, the value gets varied like this. And this binary data is again processed and it is converted into decimal and it is made into a sensible data. Here they are measuring something in terms of weight or mass. That's why it is in the application software is showing that in terms of pounds. So this is the basic phenomenon behind any ADC. Now let's come back to our slide. So now what we are going to do is we are going to show the ADC interface. So what is LDR? As I told you, LDR is a photoresistor, or it's also popularly known as light dependent resistor. So it is a light sensitive device. When I say light sensitive device, the resistance vary based on the light sensitiveness. So it works on the principle of photoconductivity. So basically, it is used to indicate the presence or absence of the light. So when I say the presence or absence of the light, we can sense the extreme darkness, or we can just sense the extreme light also. Uh, with that, so in the extreme dark, the resistance is very high. It can go up to 1 megaohm, whereas when it exposed to the light, the resistance drops dramatically. It drops to few ohms. So the range of the resistance variation is to that large extent. So we will take this uh, into our circuit into account, and we will convert this resistance into electrical output. And for this, we need to work with the LDR module. A typical LDR module will have these kind of circuitry. This is your LDR, the device that's connected here, which is basically a change in resistance device. The operating voltage is 3 to 5 volt, and output volt would be of analog type. So you can take it as 0 and 1 also. But if you take it as analog voltage, so you can process more, and you can vary the potentiometer sensitivity by adjusting this digital potentiometer size, digital potentiometer value. Now let's go ahead and look how does the circuitry looks like. So this is interesting. Now what I'm doing is I'm connecting my analog pin to the analog, and the ground to the ground, and the power to the power, simple connection. And then we will continue to have the same LED circuit. What we will do is in our code, we will see if the input value, which is coming from the LDR, if it is more than 800, then we will turn on the light. If it is less than 800, we will turn off the LED. let's get started. Let's do this particular circuit along with me. Please try. I'm back at my OP circuit. Let me delete this switch part. The whole switch part I have deleted. So let me keep my yeah, button replace with LDR this time. What I'm going to do here is, let me zoom. Let's pull the LDR device. So you can search for LDR. So you have this LDR sensor ready as such. And if you want to read more about it, as I told you, just click that. It will take you to the pin details and it will take you to all the references. And it will also talk about the connection between lux value and the resistance value, and what is the equivalent voltage it will get generated, and what is the analog reference value of that voltage. So you will get all these information. Let me close all this. So now it's time to build this particular circuit. Let me take VCC. VCC I'm going to connect to 3.3. Then let me take the ground to ground. Ground is connected to the LED ground or to the common ground. You can take analog or digital. We are going to take analog so that we'll see the capability of ADC. The analog pin is this particular pin. Let me zoom and see which particular pin is analog. 1, 2, 3, 4. Fifth pin is analog. 1, 2, 3, 4. Fourth pin is used. I'm also using that. Already fourth pin I have connected to. Okay, let me change that. Let me connect this to my fifth pin. And this to my fourth pin. So now the circuit is ready, good to go. Let's start writing the code. I hope this is clear. What we have done is, this A0 is connected to pin number 4, LED is connected to pin number 5. Other than that, I have connected VCC and ground. VCC is given 3.3 volt. So now what I'm going to do is, I'm going to change the code. So in the code, LED is 5. Let's keep LED as fifth pin. And LDR as 4. So for LED as output, this is fine. Let me remove this. Then let me continue with the code. I'm going to use serial.begin here. So just to print a message, let me put that as well. So this line is to set the baud rate or speed of the data communication between your PSP board to the computer. Then what I'm going to do is, I'm going to use I'm just going to use, sorry, this is a digital read, whereas the analog read is this code. I'm going to have a variable called input value coming from LDR. Put underscore val. So input underscore val is updated from the function called as analog read. So I'm going to read which pin. It's very simple, straightforward. It's small a. I'm going to read the LDR pin, which is nothing but my fourth pin. So now if input value is greater than 800, so this value 800 is nothing but the analog conversion equivalent of my voltage level. 800, then I'll go and I'll turn on the LED. If not, I'll turn off the LED. So this is the code, simple code that allow us to play with the LDR and get some output clone. Here, the learning is all about what is the phenomenon behind analog read. I'm ensuring again this is connected to L5, LED is connected to this is connected to L4. Now LED is not clone. I'm changing the lux value. You can able to stop this and see the serial monitor. One minute. So you can able to see the serial monitor here in this window. Let me write the serial dot write value here. Let's see what it is reading serially. So there is a error. That's why it is actually not reading a valuable information. It is reading some junk value. So it's all the same variable. Okay. So let me put a serial.println. Now every time it prints the value in the new line, we will see what is the value that's getting changed. So it is 1001 for the luminescence that we have selected. If I go, it goes to 200. If I go this side, it increases. Now, according to our code, if the input value is greater than 800, then we should have the LED glowing. So LED is connected to pin number 5, isn't it? So 8 is not glowing. The LED is connected to pin number 5 and it is properly grounded also. It's the same LED. LED is marked as output. Any findings, guys? What is mean by 800 of the input value? So 800 is nothing but, let's say, for example, this luminescence change is giving a equivalent analog voltage. So that analog representation, when I convert that analog value into a digital value, for a 10-bit ADC, it produces value between 0 to 1024. So again, that information is available from this page. So from this page, I can able to figure out if I'm building a circuit or if my voltage equivalent is 3.09 volt. So my analog read value would be 633. So when I mark something as 800, it is between 633 to 853. So when the LDR resistance is between somewhere close to 50 kilo ohms, then I'm actually making the LED to glow. I think I've connected fairly everything straightforward. Everything is connected. Let me troubleshoot this. Let me add this line. But my sensor value is changing according to my luminescence. Some problem with my LED circuit. Let me use onboard LED instead of this particular LED. Let me delete this. Let me delete this and use the onboard LED. I'm deleting this whole LED. We know onboard LED number is 2. Let's try on that. Yeah, so you can able to see the LED glowing. If I go beyond certain value, yeah, the LED is turning off. Here, now the LED will turn off. Yeah, now the LED, you just have a look at this blue color line. When the value is 108 at a very high lux level, the value goes very low. Here, 334 LED is not turning on. Above 800, the LED will turn on. So I made some mistake with the circuit on the LED. So I have deleted it and I have mapped it with the inbuilt LED. Now you can see the value actually changing. So this is the phenomenon, or this is how ADC works. So basically you are converting, you are adjusting the light level. Depending on the light level, the resistance value is varying. Depending on the resistance value, the voltage output is changing. When I convert that voltage into a digital data, it is mapped between, you can see what is the extreme value. From extreme low is 32 and extreme high is 4063. So it is mapped between my ADC range is somewhere between that. So this particular input resistance is mapped between those two values, those two extremes. Somewhere I have made 800 as a reference point. After that, the LED should turn on. Below that, the LED should turn off. So that's what I have done. So when the lux goes down, the LED is turning on. Lux goes up, the LED is turning off. So that you can see with this blue LED. So this is also working. It's a very simple understanding, but more than your understanding on the analog read, you need to understand what is happening behind this whole process. That's very important. Amit Jampa, thank you. I have connected my charger. It's already charging. We have still 1 more hour pending with us, and we have 3 more examples to be completed. One is a MQTT protocol, web publishing. Other one is an ultrasonic sensor. Other one is a servo motor. So if you have got no queries, let me move with the next example. So far, what we have done is we have tried out a switch, digital input, digital output, as well as a analog input. Now let's move ahead with the next level of device, which is the other family of sensor, which is ultrasonic sensor. Ultrasonic sensor is again a interesting device which will allow you to find the distance. It's a very commonly used sensor. You can acquire the value and you can have a smart reverse parking sensors. Your typical reverse parking sensors are ultrasonic sensors. So basically this works based on echolocation. So it's a kind of a radar system where there will be a transmitter, there will be a receiver, and there will be an obstacle. The transmitted ultrasonic waves are received back through the received back to the receiver from the sensor itself. So we will measure the distance between these two, and we will write, or we will calculate the distance or the time taken, and we will proceed calculating what is the, based on the time taken, we will know the we already know the velocity of the sound. From that we calculate what is typically the distance between the sensor and the obstacle. So here we have sensor works in such a way that it converts electrical energy into acoustic wave, the transmitter, whereas the receiver on the other end, it converts the acoustic sound into a electrical signal. So the famous module which generates which acts like a transmitter receiver is your HCSR04. It generates ultrasonic waves up to 40 kilohertz. So it goes, the working goes like this. We cannot hear this acoustic signal because our audio range is up to 20 kilohertz. So you don't hear any noise. It's completely noiseless sensor. So trigger, when we trigger this, what happens? There is a trigger input. When we give this trigger input, it generates a sonic burst or an acoustic burst of a 40 kilohertz with 8 times. So 8 times a 40 kilohertz signal is actually transmitted. Then it is reflected. So assume there is an obstacle here. It's on the obstacle and it is returning back. So what we are doing is we are measuring the propagation delay between the transmission and reception. And with this, we are calculating the distance between the obstacle and our current location. So the time taken or distances can be calculated by very simple formula. Distance is nothing but time taken into the speed of the sound. We know speed of the sound is 343 meter per second. So this quantity, time taken into speed, because speed is nothing but distance by time. So if I do this, I'll get a quantity which is only distance. If I divide that distance by 2, I'll get the actual distance. The why I'm dividing it by 2, because there is a propagation delay. It has to transmit, go hit the what do you say? It has to hit the obstacle and it has to come back. The signal is traveling twice. So we are dividing it by 2. So the code goes like this. What we are doing is we want to generate a input to the trigger pin. So once trigger pin has given some input, a short pulse like this for a 10 microsecond. So your ultrasonic sensor sound like senses and it transmits a signal, and you receive the signal with a function called as pulse in, and this particular pulse in function will give you what is the duration, and you can convert that duration into distance in centimeter, and you can do it in distance in inches. You can do that unit conversion as part of your application code. So this is how ultrasonic sensor works, and this is how you can interface the ultrasonic sensor coding as well. So the physical connection for this is very straightforward. Let me show you that this device has got 4 pins. Okay, let me show in the tool. Let me delete this. Let me add an ultrasonic sensor, the same HCSR04. Now I'm clicking this. So if you see, it has got 4 pins. The first pin is VCC, which will take 5 volts. The second pin is the trigger pin, which will start the ultrasonic burst from the transmitter. And third pin is the echo pin, which measures the eye pulse, that is the eye pulse length that is getting the distance. So this echo pin will give the electrical input once we receive the pulse. So basically what we are measuring is from the trigger, we are turning on a timer, and we are turning off the timer when we receive the echo pin. So that's how internally it works. So internally we use the microcontroller's timer to calculate the timing. So for getting the value in terms of centimeter, you want to divide it by 58, and for inches it is 148. So this is about the connection. And on the OKV side, nothing much bigger. You just have to connect each of this pin to the respective voltage levels. So it goes here. It works with, I guess it works with 5 volt. So you should connect it with 5 volt or VN basically instead of 3.3 volt. Then your trigger can be a digital pin because we are actually giving it either 0 or 1. Then echo, again it can be a other digital pin because we want to measure at when the pulse is coming in. Then ground, you can connect to a ground, which we have already done. So as simple as this 4 connection, and the code is also very straightforward. We are initiating this particular pin so that the ultrasonic sensor transmits the pulse, and we are receiving, turning on the timer, we are receiving it. So all those timer turning on operation is taken care by API, by a library function, which with the use of pulse in function. So pulse in function basically gives the time interval. I hope this is clear. Now I'll move on with the next example, next interesting example, which is servo motor. Servo motor is a very, very popular actuator. Servo motor is a very, very popular actuator, which actuates or which inherently it's a device helps in a push and control, which means by controlling the voltage level in a typical motor, you control the speed, but in servo motor we control the position. Why? Because servo motor internally has a mechanism called as servo mechanism. So basically this servo motor is a rotary or a linear actuator that allows you to control the linear or angular position based on the feedback that is coming to the sensor, that is coming from a sensor. So basically it's a motor coupled with with a DC motor with coupled with a potentiometer, so that there is a feedback always given to this motor from this potentiometer. When the potentiometer exceeds certain value, the motor switches its polarity, so the motor changes its direction. So the motor doesn't rotate 360-degree, rather it is restricted between positive 0 to 180, again 180 to 0. So how do I know I have reached that 180 level? Because there is a potentiometer, internal potentiometer, that allows me to know that. So once I reach the maximum level, so I'm actually switching my side, so I'm switching my direction or orientation so that I reverse back or I come back to 0. So this is how a servo basically works. So there are two key components, sensor, potentiometer, as well as a motor, and there is one driver, motor driver, which helps me to change the orientation based on the feedback that I'm receiving from the potentiometer. So this operation is called a servo operation, so that the input that I'm giving will serve as a reference position for my servo mechanism. So it takes the difference between the potentiometer value and the reference voltage that I'm giving and computes the error, and always try to minimize that error because inherently it has the feedback mechanism. So what do you require then for controlling servo motor? How do you take the position control? So you relatively require some sort of sophisticated controller. Yes, and there are some special types of application for this kind of servo motor, like opening the valve, closing the valve. These things can be done with the servo motor. So the servo motor, as I told you, it's unlike a standard electric motor which either starts turning when you apply power and you control the speed. It's not like that. It basically turn or changes its polarity based on the feedback. Now let's see the terminal details of a servo motor. Again, I'm going back to the tool just to show you what are the pins that you have and what you can do with the servo motor. So a servo has got 3 different pins like this. It's very simple. So you have one pin, the second pin which is positive 5 volt, and the third pin which is ground, and the first pin is PWM servo control signal. So now what you do is you just make your servo act like a sweep or generate the maximum extremes, or you can map a potentiometer, and by tuning the potentiometer you can control the position. So finally what you are doing is you are giving some sort of reference value, and the servo tries to minimize the reference value, the error between reference and the actual position. So it allows you to control the position. So here is the connections. So my input is given 3.3. This is given as ground. Let me connect in the tool as well. This is ground. This is and this is connected to the PWM signal. This PWM signal is nothing but it is generated from D2. So the connection goes as straightforward, as simple as that. But let's see the code. So in the code, what we are doing is we are including the ESP32 servo.h. So this particular library allows us to create servo objects. So this servo objects is nothing but it's similar to a data type. You can call certain functions that is written in this class, or it's an object basically. You can call all the functions that is written as part of that class. So I'm using 2 functions. One is servo.retouch, other one is servo.write. So servo.attach explains me on which pin number that I have attached my servo, and servo.write gives me what is the initial value that I'm going to give. If I pass this value, it directly takes the angle and it goes till 180 degree. And if I pass this value 0, it comes back to 0 degree. So let me, it's being a simple code, let me write this. So I'm going to use the servo object. So I'm including the servo library. Okay, it is included. Now let me go ahead and create the servo object. I'm naming it as servo only, or SRV. Now here I'm saying that SRV is attached to pin number 2, and its initial value is 0. After setting the initial value, let's give some initial 2 seconds of delay because it's a mechanical device. It has to go to that particular position. It takes certain time. It has its own moment of inertia. Now let me write the actual code. So SRV dot write from 0, I'm moving to 180 degree. Then let's give a delay of 1 second, then again ask it to jump to 0 and give a delay of 1 second. That's it. Let's try to run this code. Okay, I made a mistake. Now it should work, I guess. Yeah. In this way, you can add the library. I have added the library. And am I missing something? Okay. Let's attach. And here I missed the semicolon. So you can able to see the servo is rotating between 0 to 180 degree. Now, if I change this to 90, you can able to see that it rotates only till 90 degree. Yeah. So from 0 to 90, it is going. That's it. So in this way, you can control the position of the servo motor. Now let's get started with that's about the position control of the servo motor. Now let's get started on the MQTT part. So about MQTT. So what is MQTT and why it is used and why it is very popular in the IoT applications? MQTT stands for Message Queuing and Telemetry Transport Protocol. It is basically a messaging protocol, so which allows you to exchange information between a cloud and the node. So basically, it is designed for constrained devices which has very low bandwidth. Or this particular protocol is a very lightweight protocol which enables you to transmit messages at a very low bandwidth. So it's a perfect solution between exchanging data between multiple IoT devices. So if you want to exchange values between IoT devices or a node and the cloud, this is a perfect and simple way. So this communication works based on two things. One is publish and subscribe system, which means it's very similar to your YouTube. In YouTube, let's assume that you are following a channel and you are subscribing to that channel and somebody is publishing the content. So based on their content publishing, you get a notification and you access that. So since you are a subscriber, their content is pushed to you or is updated to you in a live way. Here is also this communication works also on the same basis. The devices uses or some devices will publish certain specific messages, which is called topics. All the subscribed nodes will receive that particular message. This architecture is used in many other software frameworks, used in many other uh, devices. So it's very simple, straightforward. Any subscribed system will get the updated published message from a device who is publishing it. So why MQTT? As I told you, it is a lightweight network protocol, which is based on the publisher and the subscriber manner. Here the broker receives messages from all the clients and transmits those messages to the destination client. So ideally, there would be an intermediate broker who helps in transmitting and receiving, or who streamline this. So the whole MQTT is nothing but it's a message queue. It will have a queuing. Your message is stored in those queues, and the broker takes care of segregating and passing that to the respective destination. Here, the sensor gather data and transmit those data to the MQTT broker. So, which in turn sends that to a SQL database. Or assume your application is running in the cloud, which is created from a SQL database. So, your application will be subscribed to the node or to that particular sensor, where your broker sends streamline that data and send it to the SQL database. Here are some examples. Say these are the application services or applications that is hosted onto the cloud. It has subscribed to some node. Let's assume a node is publishing 20°. So that information is actually subscribed, or that information is actually passed via this MQTT broker to all the subscribers. So who are the subscribers here? This application could be subscribing to this node. This application should be subscribing to this node. So when it publishes a data, that's updated at all the subscribers level. So here the device, who are the device? The publishers are the device, the nodes are the device. They gather the data. What data? Temperature data from the sensor that is connected, and they transmit the data to the MQTT broker. So this MQTT broker allows the subscribers and transmit, in turn sends the transmitted value from the publisher to the subscribers. So it is lightweight, efficient. These are some important advantages of MQTT. They are bidirectional in terms of communication, which means some messages can be passed from the subscriber to the actual publisher. So MQTT allows messaging between devices to cloud as well as cloud to device. So this makes easy broadcasting of messages, and this protocol, since it's a lightweight, it can be scaled to millions of things, and reliable message delivery is possible. Then you have reliability of message delivery, that's one thing, and you have MQTT that's defined at a service level, so where at least once, exactly once. So you can improve the service level, and you can ensure the reliability of the message, and it is security enabled by default. The messages that's going are encrypted based on TLS, and it is authenticated. It's one of the modern authentication mechanisms. So the in between messages are encrypted, so we can rely on this protocol, and it supports many unreliable network also. Even if the network is down, then MQTT offers a better possibility. So let's build one small example. I'll show what exactly we are going to do. We are going to publish, or we are going to subscribe a node which is made of ESP32 to back onto the let's say to a subscriber. There is a MQTT broker and there is a subscriber. So we are creating a service, as well as we are passing that to the MQTT broker, and depending on the message the subscriber is putting, I'm going to control the LED, or I want to digitally turn off something from my subscriber end. So if as a subscriber, if I pass the message off, LED will get off here. As a subscriber, if I pass the message on, LED will get on. So which means anybody at any location can able to control the LED. So that's a one interesting way that even we can try. I'll build the circuit. Somebody who is connected remotely in the forum, I'll give the link, attempt to create or attempt to control the LED that we are making in the simulator. So for that, we will make use of Hive MQ. So this MQTT broker will supply or will help us to connect to the client, as well as will help you to connect to the or put the messages. Let's have a quick look at the code. The code is slightly comparatively bigger, but it is again simple to understand. So we need to add two libraries. One is Wi-Fi.h, other one is um, PubSub client. So it's publisher subscriber client.h. So to add a new library to workplace simulator, what you have to do is you have to go to the library manager and you have to click delete all the libraries. If you have anything, you can add library. Here you can look for uh, PubSub client. That's it. You have added the publisher subscriber client library so that you can reuse that library as in your code like this. I've included. Now I'm assuming that the subscriber as well as the publisher are connected to the same Wi-Fi. So we are using Wi-Fi, so which means to the same network. So the SSID is weakest because if you use this credentials only, we can able to use this MQTT Hive dashboard. So I'm just going with the MQTT server as broker.mqttdashboard.com and no password. And the port that we will be using is 1883. Then we will be using client ID and MAC ID. Once this is done, I'm just using the LED from LED pin 2. Let's ensure that we have a circuit that is connected to pin number 2. So by default, pin number 2 is connected to this particular LED. Let's not worry much, or let's not put effort on building a new circuit. What we are going to do is we are going to pass some messages once the Wi-Fi is connected. So this is the initial setting up duration. What we are doing is we are connecting to the Wi-Fi, connecting the node to the Wi-Fi. We are assigning getting the IP address. We are getting the MAC address of that particular device. So IP address is assigned at network level. MAC address is assigned at the device level. So which means MAC address is very, very unique to that particular device. Then we will set the client port details. We will call the callback function and we will make the LED glow. So sorry, we are setting the LED pin as a output pin. This is our setup function. So inside this, now I have called two functions. One is Wi-Fi connect, other one is set callback and set server. Let's see the definition for all this. Wi-Fi connect, I'm actually passing the SSID and password and beginning the Wi-Fi. So there will be a loop. So till the Wi-Fi is getting connected, it will run. And we use other function called MQTT reconnect. So I'll explain the code later. That is used in the loop. Then this is a callback option. So in the callback option is the callback code, what we are doing. So we are calling here at the client side, we are setting the callback function. So it takes two inputs, two string character string. One is byte string, other one is character string, which is topic and which is the message. And third input is the length. So I'm just printing the topic name. I'm printing the message, and I'm having that message as a string. So this is just to send that string to the serial println. Then I'm actually comparing if the string topic name is topic name dot slash LED. If that is the case, I'll change the output accordingly. I'll change the output message. I'll print this line in my terminal, and if ST message is on, which means the incoming message from the publisher, if that is on, so our LED pin is set high. If that message is off, the LED pin is set low. Then we have a loop. So in the loop, we will call the function MQTT reconnect if the client is not connected. If it is connected, the client loop would be continuously running. So which means always the client end to connect with the Hive. Now let's go and create this code and put this code. I have this code since it's a bigger code, I have already written the code. So I have this code. Let me copy this code and put it here in the tool. And let me ensure that the libraries that I have used here is added here. Yeah. So I have ensured that Wi-Fi is added, pub sub client is added, then all the functions are there. So LED pin is 2, LED pin is internal LED pin is there. So let me run this code. So parallelly, what I'll do is I'll go to the MQTT broker page. So the MQTT broker page is here. So this allows me to connect to the simulator. So it's trying to connecting to the guest. So you can click connect. It is connected. Now, what you can do is you can close all this. You can add a new topic. What is that topic name that we have given in the code? The topic name is topic name / LED. So it is topic names / LED. I'm subscribing to that. Now the message is on. If I expand this, I can able to send message from here. So let me put topic name LED, and I can send message to this. Currently, I can see, go here, see the LED is turned on. LED is turned on. If I pass the message off, and by clicking the publish, you can see the LED is turned off now because the message has arrived from the subscribed topic. Now let me go back and turn it on. Let me put the message as on. It is on now. The LED is on now. So in this way, you can have a circuit that is built, that is published to a service through a MQTT broker, and you can able to control that from this kind of MQTT brokers by publishing to that service. So it's very simple. Now I'm publishing certain message here, which is the topic name / LED, and this is to which this node has subscribed. So every time it is trying to get the message from topic name, and it is running. If I make it as off, so the LED goes off, and here you could see the message. I hope this example is clear. So if you have any queries on trying this, please do let me know. I'll keep these slides. You can have this recording. The detailed code is there. It's given. You can take the snapshot. Purposefully, we don't want to share the coding files. Let's practice from your end. Type the code, debug, like make errors, fix the errors. Then try to get the output. That's the intention. So I'm just keeping the code for you for some time so that you can take some snapshots. So this is on the Wi-Fi connect and MQTT reconnect, and this is on the main loop. So that's it from my side.